Okay, then Bismillah ar-Rahman ar-Rahim. So let's start with this CO2. Uh, the statement of the CO2 is translate the predicates and quantifiers. In some different examples, these predicates and quantifiers will be given in some different examples or questions, and then you have to do what? You have to translate or convert these predicates and quantifiers into English sentences. Or in short way, you will have some mathematical equations in which you have these predicates and quantifiers. You have to convert those mathematical equations in English sentences and vice versa and opposite. English sentences will be given to you and you have to form or build the mathematical equations using these two concepts, predicates and quantifiers. So, okay, again, I will update this link. This link is starting from, I think, slide 16 or 15. So when we will record up to slide 15, 16, I will stop recording, and then after the lecture, I will update these slides also with the updated link. So now, before starting the topic of this predicates and quantifiers, we already have studied propositional logic in CO1. Whatever you have seen in the CO1 related to proposition, what is proposition, and then how you can convert a proposition into the form of a variable, and then how you can connect them or like that. You have studied these things in CO1. So that is called propositional logic. So, and in CO1, somewhere at some slide, we already studied that this propositional logic has some deficiencies, has some limits. And due to those deficiencies and limits, sometimes we cannot express the true meaning of some sentence which are given in some natural language, which are given in any language like Arabic or English or whatever. So sometimes we cannot convert the true meaning or the actual meaning, or we cannot handle the actual meaning which is given in the sentence into a mathematical equations. This is the deficiency of this propositional logic. And then what? Then comes the predicate logic to cover up this deficiency. The things that you cannot cover in propositional logic, you can convert them, you can cover them in predicate logic. So predicate logic is again something like propositional logic, but its level is a little bit advanced. And here you can express the meaning of sentences at a wider range, And when you can convert a sentence into the form of predicates and quantifiers here in this field, then you can do what? Then you can analyze the values of those predicates and quantifiers. And then you can analyze the connections, the relationships between those different things for which you will introduce these predicates and quantifiers. So this is just a definition. You only have to know that propositional is some field in which you have limitations. Those limitations are covered here in this predicate logic, but again, it has its own limitations. Okay, it has its own drawbacks. So let's start with these predicates and quantifiers properly. And here we have the definition of predicates. What is predicate? So when some sentence will be given to you, then you have to identify, or just leave it for a moment. When some sentence will be given to you, there would be two things in those sentences. The first thing would be variable, and the second thing would be predicate. For example, if you have this sentence in front of you, x is greater than 3, then clearly x is something which is called the variable, in this sentence. Sometime you will not have something like X, Y, P, Q, R, S, T in the sentence. Then what you have to think by yourself, what entity or what thing use you can use it as a variable. So you have to identify variable. First thing, you have to identify variable in the sentence. But in this example, it is very clear because it is for your understanding. So that's why. So that's why example is very clear. So here X is a variable, which is the subject of this sentence, which is here. Here in this sentence, it is acting what? It is acting as the subject of the sentence. But subject of the sentence is not the condition that you have to sort. You have to find uh, just variable. And when you will see two or three sentences in next example, then you will identify variables quite easily. But predicate, okay, predicate would be an issue for you always when the sentences would be complex. Here the sentence is easy. Normally in linguistics mean the study of languages. Either it is Arabic, English, whatever the language is. Normally predicate is a verb. Is a verb. Verb normally tells us that what is the subject and what is the object or other things of the sentence. Normally, verbs gives us that information. For example, here X and then normally predicates start from the verb. So is a verb. So then you can say you have something from the verb up to the end. You can call it predicate without going into details. So you have to identify two things. One thing is variable, and the rest of the thing in the sentence is your predicate, is the story. That story is called predicate. Basically, I have to use the word concept, but maybe it will confuse you. So that's why I'm using a general word story. So you have the variable and the rest of the thing except variable, then rest of the thing is your story. That story is called predicate, and here you can see what is predicate. So is greater than 3 is then it is left, so that would be called what? That would be the predicate. That would be the predicate, and it will give you the concept that it will contain some information or some property that would be the property of that subject, that variable, the property that subject has. Anyhow, if you don't understand, leave that, because these are something related to linguistics. Anyhow, so you have to identify variable and you have to identify predicate, nothing else. And how we can represent predicate here in this predicate logic? We can represent predicate with the capital letter, like you are seeing capital P here. And then you have these parentheses. These are something fixed, okay? And here you must have some capital letter, P, Q, R, S, T, but capital. And then you have the parentheses, and then between the parentheses, you have to write your variable. You have to write your variable. This is the notation which you can use here in mathematics to represent a predicate. And then this whole P, how you can read it? P of X. Or you can read it propositional function P at X. These are the two readings. So whatever reading you like, you can opt that. So the short one is P of X. And what is the meaning of this P of X? The meaning is, if we are taking this example, then the meaning is the whole sentence. X is greater than 3. X is greater than 3 because you are taking P as a is greater than 3 and X is that variable. And how you can read that? X is greater than 3. This is how you can read it. Okay, now this is the proper definition for the predicate in discrete mathematics. In discrete mathematics, not in linguistics, okay? In discrete mathematics. Linguistic definition is different. That is the verb actually. Who tells the what is the who tells what is the subject, what is the object, what is the indirect object, or what is the predicate links, these kinds of things. Anyhow, in discrete mathematics, if you will have some logical expression means what? Anybody? Yes. That is a proposition. That is the definition of proposition. It can be true or false. But this is logical expression. So logical expression is any mathematical equation that you normally build. Okay. So so a logical expression, which means that any mathematical equation that you will form using propositions, predicates, or quantifiers. So a logical expression that will contain that variable. So now this is a logical expression. Okay, the small one. It's not a big equation. It's just small one, and it is containing what? It is containing variable x. So a logical expression that will contain some variable, and this logical expression I can call it a proposition when I will assign some value to this variable x. When I will assign some value to this variable x, then this proposition can be true, can be false. Because it is then it will become proposition, then it will give you true or false answer. So that whole thing, that logical expression is then called predicate. It's called predicate. And now we can also use any number of variables here within these parentheses. We can also use any number of variables within these parentheses. Here in this example, we have only one variable. But if you can also write something like that, q into x comma y, or q of x comma y. And this is for the sentence what? If you have a sentence like that, x is equal to y plus 3. This is sentence, okay? This is sentence. And then here you have two variables, x and y. And is equal to y plus 3. The rest of the story you are covering here in this q. You are covering the rest of the story in this predicate q, and here you have two variable x comma y. And then how you can say it, actual meaning of this, x is equal to y plus 3. This q is a predicate, okay? So this capital one is the predicate and these small ones are the variables. So this is just an example that you can use one variable or two variables. Actually, any number of variables up to n. You will see this definition again. So now let's see this example. This here the question is lengthy, but the solution is within 2 lines. So here in this example, a predicate is given to you, and the predicate is capital A, or you can say A of C comma N. And this predicate represents the statement, and statement means sentence. And what is that? Computer C. Computer C is connected to the network N. Here the sentence is ending. So this predicate is representing this sentence. If this sentence will be given to you, how you can make a predicate. So C is one variable, then network N is one variable. It is written there, so that's why it's easy to identify. It's easy to identify. If it is not written, then you have to assume computer is, then some information will be given to you. Just wait. So here these C and N are given in the sentence. So that's why it's easy to identify that these two are variable. And then from the verb is connected to, mainly is connected to. This is your predicate. This is your starting from the verb. So you have to look at the verb, and then it will be easy for you to identify that where is the predicate. So then you can write like A into C comma N. So what it means? It means that this computer C is connected to network N. Okay, where C is variable representing computer, N is variable representing network. So this is the question which is going on. And now we have some extra information in the question. Suppose that computer, and the name of the computer is Math1, is connected to network campus 2. So this Math1 is connected to what? Which network? Campus 2. But not to the network campus 1. So this is the information given here in this question. And now the actual question is starting from here. What are the values of this predicate with values and this predicate with values? Here now you don't have the variables. Here the values to those variables are assigned. Math 1 is a value given to C. Campus 1 is a value given to N in this logical expression, in this mathematical equation. Similarly, math 1 is a value given to computer. Campus 2 is a value given to the network. So now you have to give answer of this question, that what are the values of this and that by using this existing information. That is easy. You know that. What is the meaning of this one? The meaning of this one is math 1 is connected to campus 1. Is it true according to this given information? No, it is not. It is false. So that's why we are writing it here. And similarly, math 1 is connected to campus 2. Is it true? Using this existing information in the question, yes, it is. That's why we are writing it true. So here we are again converting sentences, but in different way, using predicates and variables. Before that, it was only variable, propositions, and connectors. Now we will have connectors, we will have predicates, we will have variables, we will have quantifiers. But let's see how it will be. We are just starting, so that's why example is quite easy. Now, this is extra information, not linked with this question. Additional information. So if you can have something, some predicate with n number of variables from x1, x2, and so on, xn. What it is saying? It is saying that the predicate can have n number of variables. Can have n number of variables. And how you will say it? P is, okay, I can call it propositional function P at n tuple. Tuple normally means a row, record. So it is a term that we normally use in databases. So propositional function P at n tuple. So, and that tuple, that row record is containing what? N number of variables. So that's why we are saying it n tuple. This is one way. Another way you can say this thing is this P, also called n place predicates. You can say that this P is a what? N place predicate. This is a n place predicate P. So n place means this predicate has n places for the variables. Similarly, we can call it n-ary predicate, which means this predicate has n dimensions, like binary, ternary. So that is that n-ary. If n variables, n-ary. So anyhow, this is just the information. You only have to see it at once so that it will come again in the literature. Then at least you will understand what it is saying. Then there are easy examples like this from 1 to 3 and 5 to 7 in the book. You have to read it by yourself. And now we are moving towards the definition of quantifiers. We have just started. And in the start, we are learning what is predicate, what is quantifier, and then we will go on with the proper exercises and with the different subjects. So now, quantifiers. If I say the word quantify, then you can understand that if I say quantify this amount of wheat which is lying here, then you will have some weight machine and then you will quantify that wheat, how much kilo that wheat is. So finding that kilograms of that wheat is what you are quantifying. So that is the same concept. Quantifiers. You will have some quantifiers. In mathematics. We will study 2 quantifiers here. And those quantifiers will do what? They will do quantification. Quantification of what? Quantification of values for the variables that exist in some predicate. It will quantify that what different values you can assign to those variables in the predicates. So that's why now if you will read this sentence, then you will understand what is quantification. Express the extent, express the limit. Express the limit to which a predicate is true over a range of elements. So you will have the predicates, and then that predicate will have some variable, and then with that variable you will have some quantifier, and that quantifier will tell you that from some given domain, what are the different values you can assign to that variable? It will give you that range. It will give you that extent. It will give you that extent. And when you will have the answers for all possible values for that variable, that is what that quantifier is giving you, that answer that you can assign these values. That is called quantification. Anyhow, in English, you will see these words, and all these words are the words for for this concept quantification. What are those words? If you will see all, I want all of them. So you are saying I want all. So this is what the quantification concept. I want some. So this sum is a word also used for quantification. How much you need, how much you want. Many, I want many. So these different words. In Arabic, you may have the equal words with that, and that all normally called quantifiers. In linguistics, we normally call them cardinals, ordinals, sometimes quantifiers also. So these are the, but anyhow, so that's why you have this word quantifiers. All, some, many, none. I don't need anything. I don't need none, you can say. Few. So it means maybe bas. What is the word? Khalil. Khalil. Okay. Okay. So few. So these are the English words which normally there would be some else also. But if you will have the concepts like that, then you can convert those sentence into quantifiers. There are two types of quantification. First one is universal. Second one is existential. And we have a symbol for universal and we have a symbol for existential here in discrete mathematics. Now, this is just a definition, not linked with this one, because we are in a new field that is called predicate logic or predicate calculus. What is that field? What is that area? So that is the area of logic which deals with what? Predicates and quantifier, two things, which deals with in which you will have mathematical equations including predicates and quantifiers. Anyhow, that is called predicate calculus or predicate logic. Now, what is universal quantifier? This symbol, I am sure that you have seen somewhere in mathematics. This symbol, I'm sure that you have seen somewhere in the mathematics. So this inverted A, that is called universal quantifier. That is called universal quantifier. We normally use this quantifier with some variable of a predicate. And if, for example, you have something like that, P of X, that is what? That is a predicate with some variable X. And if we will use this with this predicate or this universal predicate, universal quantifier, if you will use, we will use this universal quantifier with the variable of the predicate that is X. How we can use? We can use it like that. For how we can read? For every X, P of X. This is the representation in mathematics. How we can represent it? We can use this quantifier with the variable, not with the predicate, okay? You cannot use this quantifier directly with predicate. Like, for example, if this is not available here, then this for every is with P, not with X. So, no, it's wrong. You always use quantifier with the variables of the predicate. So this is the mathematical representation. But what is the meaning of that? The meaning of that, how we can read it? For every X, P of X. Or you can say for all X, P of X, both are written here. But what is the meaning? The meaning or the definition of this notation is that for every X, P of X is true. What is the meaning of this? We want to say that for every X, P of X is true. Or I can say for every value of X from the domain, this P of X is true. domain will be given to you in the question, that what is the domain. For example, set of all integers is domain, it will be given to you. Set of real numbers, domain will be given to you. It can be anything, it can be anything. In the question, these domain will be given to you. Sometime it is called domain, sometime it is called universe of discourse, or simply universe. These are the different names we normally use for the domain. Anyhow, so what is the definition? If we will use this universal quantifier, that would be predicate is true, p, which is that, which is v, which is p of x, is true for all values of x from the domain or in the domain. And this is the mathematical representation. And how we normally say it, this is that written here. What is the meaning? If for every x p of x is there, if you have this statement, when this statement will be true and when this statement will be false, let's see that. Let's see that. It is very necessary to understand what these statements are saying. Only then you can identify it is when it will be true, when it will be false. So if you have for every x p of x, what is the meaning of that? The meaning of that is for every x, this p of x is true. If, now I'm using the word if for every x, this p of x is true, then this whole statement will be true. Okay. Here it is written, p of x is true for all x. For all x's, you can say. For all values of x. If it is, this p of x is true, if predicate is true for all values of x, then this statement will be true. And when it will be false, to make any theory false, you only need one evidence. From that, from all those values, from that domain, you only need one evidence to make that theory false. So now this is one theory written in mathematical form. So if any value, if p of x is false for any one value of x, then this whole theory will be false. So that is written here. There is an x, one x. X is a variable, it will have some value in it. There is an x for which this p of x is false, then this whole theory will be false. Okay, so this is the false condition of this statement. And when it will be true, to make this theory true, you need all values, for all values, p of x must be true for all values. Anyhow, this is the concept of, for this reason we normally use this quantifier, because it is for all, for every something. It is not representing the meaning of some or few or whatever. It is representing the meaning of what? All. So let's see this example. But here you see that for quantification we have this word all, some, many, none. But here we are studying quantifiers. We are not studying universal, okay? So that's why all these words are there, because these words are representing all quantifiers. Anyhow, but here we are in the category of universal only. So let's see this example. Let p of x, okay, that would be some predicate with some variable x. I don't know, but this is some predicate with variable x. So let p of x is the statement, and that statement is given not in English sentence, but in a mathematical form. It can be. Propositions can be a sentence, proposition can be a mathematical formula or whatever, because you only have to see that either it is becoming true or false. And these predicates, when they are in the form of logical expression, these can also be propositions, which means you can say them. These can also give you the true or false value only if the value to the variable is assigned. This is the definition of the predicate. Anyhow, let p of x is the statement, and so now the mathematical sentence which is given to us, this is given. And now we are representing that sentence into this predicate form p, and this x which is acting as a variable here, we are representing it within the parentheses. Okay, So this is the predicate for that sentence. Okay. Then what is the truth value of the quantification for every x p of x? If we will use for every x p of x with this predicate, then what would be the truth value of the quantification? What would be the truth value of this here? Because you have used quantifier, so what would be the truth value of this, where the domain consists of all real numbers? So now domain is given. Domain is given. From the domain you can take any value and you can assign to the variable, and then you have to check that your p of x is true or not. Now again, I am repeating. I am bound to sit here, but I am repeating that step, how you can identify these things. So you have to identify domain from the question. That is very important for these type of questions, predicates. You have to identify what is the domain, and then you have to identify what is the mathematical formula. If it is available, then good. If not, you have to make it by yourself. And then you have to identify what is the actually given sentence, either in the mathematical form or in the English form. So that is that sentence given here. If this predicate is already formed, then it's okay. If not, you have to form it like that. So you can say, so all that story, x plus 1 greater than x, I can write it in words. X plus plus 1 one, x plus 1 is greater than x. When is will be, is the starting of the predicate. Anyhow, so now this is the predicate. So I am representing that predicate with p, and this variable x is representing with x. We have to find the value of this. So if for all values of x, if p of x is true, then I can say this story would be true. The question is, what are the truth values of quantification? We have to find this one. We know the definition of this one from the previous slide. From the previous slide, we know what it means. So now we have to show that when it will be true and when it will be false. This is what, when it will be true, when it will be false. This is what you can find the truth values for that, for that thing. So anyhow, so now when for all values of x, this predicate is true, then this story will be true. And when for any one value, this p of x is false, this story will be false. So you have to do what? What are the truth values? So you have to find these truth values. Either this theory is true or false. Domain is given, all real numbers. Real numbers are what? 0.25, 0.45, 0.43, 0.5, 0.75. These are real numbers. So now you can take any real number from this domain and you can put that value here in the equation, and then you can see either this equation is true or not. Because what is p of x? P of x is actually this equation. We have to check greater than is equal to x. Anyhow, so if I will take 0.5, then 0.5 plus 1, 1.5, it would be greater than x. What is the value of x? 0.5. So it would be true. If I will take 0.75, that 0.75 plus 1, it will be 1.75. And what is the value of x? 0.75. So it will always be greater. It will always be greater, whatever the real number you can take from this domain. Because we are adding 1 into that real number, which will make this left-hand side, always greater than this right-hand side. So now, so it means for it is becoming, and what is this? This equation is what? This is p of x. It is given here in the equation. It is p of x. Now your p of x is true for all values of x in the domain. Now you cannot write all values, okay? You only have to check 3-4 values and then you have to give your answer. So now solution, because now you can write, because this p of x, which is this equation, because this p of x is true for all values from the domain, for all real numbers x, because this p of x is true. Therefore this theory, this quantification, you can say, therefore for every x, p of x is what? What is the truth? Is true. Is true. This is that definition. When p of x is true for all every x, then this will be true. And if for any value it is false, then this will false. Easy. Okay. Now this question is ended here. Now this is some additional information that if domain is empty, then what would be the situation? If this domain in the question is empty, then what would be the effect of that? If domain is empty, then we don't have any element to make this theory false. Normally, definition, what is the meaning of that? The meaning of that is p of x is true for all x. We have to check that it is true. So by default, it is true for all x. And how we can make it false? When we will find some value for which this p of x is false. And when the domain is empty, we don't have any element to make it false. So that's why it will remain, by default, it will remain true. That is what written here. That is what written here. If domain is empty, this theory will be true for p of x, because we don't have any element in the domain for which this p of x will become false. And if you have n number of variables, x1, x2, xn, for this statement, for every x, p of x, if you have n variables there in between the parentheses, then you have to do check. Then you have to do what? You have to check this predicate for first variable, for second variable, for all variables, and for every. And when these all predicates will be true, only then this theory would be true. This is what the definition of this thing. If you have multiple variables and you are checking this universal quantifier, then predicate must be true for all variables. Therefore, we are representing it with and. And conjunction is between all these parentheses. And when all conditions, when all predicates would be true, then this universal quantifier would be true. That is very much similar to your previous definition. So, universal quantifier has a conjunction between all the predicates when the number of variables are more than one. Okay? More than one. This condition true, and this condition true, and this condition true, up to n condition true, then you can say that theory is true. Now, what are the words available for this universal quantifiers? You will see the word. If you will have the concept like that in English sentences, then you can convert them into universal quantifier. All of, for each, given any, for arbitrary, for any. These are the different words that you can find in English sentences. For all, for every. Most commonly used are for all and for every. But if you have these words, and if these words are giving the concept of totality, totality means whole, all, then you can convert them into universal. Because there are some words like any, which is ambiguous here, which is ambiguous. Sometimes any gives the meaning as a whole, sometimes only some. Khalid. So, for example, look at this sentence. I want any food, and then you have, do you need any bread? For example, I want any food. What it means? You can give me any type of. All foods are permissible, are allowed to me. Huh? And if you have this sentence, do you need any bread? So if you are at my house as a guest, and I can ask you, do you need any bread? So it means a few amount of bread, huh? Not all the things which are available at house. Huh? So that's why the word sometimes can give you ambiguous meaning. So you have to understand what is the meaning there actually, and then you have to use that quantifier accordingly. So now another example. What is the truth value of for every x p of x? Where p of x is what? P of x is this statement: x square greater than less than 10. And the domain consists of positive integers not exceeding 4, not more than 4, up to 4. Positive integers, it means 1, 2, 3, 4. Positive integers. So you have to, what are the integers then? Not exceeding 4 means 1, 2, 3, 4, and no more than 4. So you have to stop there. So these are the values in that. So you have to identify that this is the domain and the p of x is given. And the question is, what is the truth value of that p of x with the universal quantifier? And you know that what it means. So if you know the definition of this one, then you will not feel any difficulty. If you don't know the definition of that, then you can answer anything. There are two possibilities, true or false. So then 50-50, huh? But here, if some student knows all the thing, he will give the answers like that. He will give me the domain. What is the domain actually here? The domain is 1, 2, 3, and 4, not more than that, according to this, not exceeding 4. And what is the definition of this for every x p of x according to this previous information? This is conjunction of all predicates. So that's why we are writing for every x p of x. So we are writing, we will check this predicate with value 1 and we will check this predicate with value 2, with value 3, with value 4, all these values and a and between them. So actually this is the understanding now. And now for 1, if you will put 1 square, 1 less than 10, true. 2, 4, 4 less than 10, true. 3 square, 9, 9 less than 10, true. And 4, 4, 16, 16 less than 10, no, false. So now you have found one value for which this p of x is what? False. So only one evidence is enough to make something false, to make this theory, not something, to make this theory false. So as for p of 4, the statement 4 square less than 10 is false. So that's why we can say that this theory for every x p of x is what? False. Is false. This is the final answer. But now this answer is very much stepwise. I'm not giving only this false or true answer like you, huh? You will give me like that, for sure. Not all students, but maybe half of the students, they will only write true, and then they will go to the next question. And then they will expect that the teacher will give me the full mark. I will not. Okay, you have to identify domain, you have to, but when I will see that most of the students are failing, then I will give you. But if I will see that now this is not the situation, half of the class has given a proper answer, then I will not give you the marks. Okay. It depends on the situation. So now example 9, 10, and 12. So these are similar examples like that. You read it by yourself. And when this CO2 will be finished, then I will take the quiz from this CO2, okay? But it's just a start. Then there is another example, read it by yourself. It's easy. What is the truth value of for every x square greater than x? So now here something written differently. So you don't have to do any mistake here. For every x, we know that quantifier is always used with a variable. And after that, we normally have the predicate. So now this is the statement. This statement, x square greater than or equal to x. This is basically equal to what? P of x. But to give you a dodge, here we have not written P of x. Rather than we have written here the actual state. And then some students will be in a confused state. What we have to do here? We don't have any P of x here. That is P of x. Written in different way. Okay? Written in that this portion is what? P of x. So what is the truth value of for every x p of x if the domain consists of all real numbers? So all real numbers. So you can check. If you will give, okay, you can check from 0.25, 0.5 or whatever. So 0.5. If you will give 0.5, 0.5 square is what? square, it would be 0.25. It will be reduced. Okay, this is mathematics. Look at it. 0.5 is a greater value. And then when you will take a square, it will be reduced 0.25. It's what? Anyhow. So when you will take the square of this 0.5, so x is 0.5, here x is 0.5. But here when you will take the square, it will become 0.25. And 25 greater than or equal to 0.5? No, false. This p of x will be false. So for the first portion, if the domain is all integers, when you will take this 0.5, the statement p of x is what? This p of x is this. P of x, 0.5 square greater than 0.5. This would, I have not written it like 0.25. You can do it by yourself. So this value will become what? 0.25, which is less than 0.5. So then this would become false. Hence, I can say that for every x, p of x is false for real numbers. And similarly, for all integers, it is answer is right there. You can read it by yourself. Existential quantifier. Existential quantifier. Now the symbol is changed. Existential. The name is also changed. Existential. Why existential? Because for reading we will use there exist. Okay. What is the definition of this existential? So how we can use it? We can use it like that. There exist x p of x. We will shortly say it. There exists x p of x. More detailed one, there is an x such that p of x is true. Or there is at least one x, at least one value is needed. If more, then alhamdulillah. But if one, then it's okay. There is at least one x such that p of x is true. I have not written here true, but it is understood through this definition. There is an x, one x for which this p of x is true. There is at least, you can also use these words, at least one x for which this p of x is true. Or you can say, for some x, p of x is true. This is the meaning of this notation. And now this is the definition. If you will read it properly, what is the meaning of that? There exists at least one element x in the domain such that p of x is true for that. So now here for this symbol, you only need one value to be true. And for that previous symbol, all value to be true, then that theory true. But here, if one value true, this theory will be true. And now focus on this second part. First one we already have seen in previously. Here I have cut this picture into half, so that's why you will not see the existential up to this point. And here that picture is complete. So this thing we already did. And we are here. There is an x p of x. How I can read it? There is an x p of x. There is an x p of x. And when this will be true? When you will find that one value of x for which this p of x is true, then this whole theory will be true. This is mentioned here. There is an x for which p of x is true. And when this theory will be false? When you will not find any one value for which this p of x is true. When you will not find any value for which this p of x is true, it means for all values of x, p of x is what? False. 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 Just think, okay? There is quite a clear chance of doing mistake in these definitions, okay? If you will think properly, then you will not do any mistake. Yes? Yeah, you can say. Yeah, you can say. So when it will be false, when p of x is false for all values of x, then this equation theory will be false. Now, example. Let p of x denote the statements. Now, this is your p of x. This statement is given, which is p of x. What is the truth value of this for there is an x p of x? Now, What is the truth value of this? Where the domain consists of all real numbers. Okay, all real numbers. If you will put 0.25 greater than 3, no. 0.5 greater than 3, 1 greater than 3. 1 is also a real number, huh? 2. So then we will take these one. 2 greater than 3, 3 greater than 3, 4 greater than 3. So we have found now one value for which this P of X is what? True. So that is enough. So this means that this theory is now then what? True. Any student who is not understanding, any student, honestly, friendly, frankly, any student who is not understanding, just raise your hand. Because this is the time I can be slow. Next, when I will pass this step, I will not come back again here. Even there is no revision at the end because we will trying hard in the end to finish this course. And all the subjects in BS, if the teachers will teach them honestly, it is very much hard to finish those courses within a semester. Well, this is I'm saying truth. I'm not using any statement against others, but I'm just saying it to you. Here, the courses, if you will look into the contents of the courses, that is very much detailed. But when you normally study, where are those contents? You will not see those contents. This is what happening. So anyhow, so P of X, according to this question, P of X is what? This is the P of X. And when you will put X is equal to 4, this will become what? True. So that's why you can say this theory will be true because we need only one evidence. We need only one evidence. Now extra information. So this theory, we need only one evidence to make that theory true. So if the domain is empty, we will not find that element to make it true. Okay. So by default, this theory will remain false. And if the domain is empty, we will not find that one element for which we can say that this theory is true. We will not find that element if domain is empty. And if domain is empty, then you can understand that by default it is false. And okay, and if you have n variables, then you don't have a conjunction between them. You have a disjunction between them. You have to, because you need only one variable. If that variable would be true, that theory would be true. So that's why you have disjunction. And there is an example 15 in the book. You can read it by yourself. That is the easy one like that. Now another example. What is the truth value of this? There is an x p of x. If p of x is this, p of x is given, and the universe of discourse is what? Positive integers not exceeding 4. What is the universe of discourse? What is the other word for universe of discourse? Domain. I told you domain or simply universe or universe of discourse is the three different names for the same thing. So P of X is given, domain is given, and quantifier is given. So now we can find either it is true or not. So we have to, what are the values? Positive integers not exceeding 4. These same values, 1, 2, 3, 4, not more than 4. So now how I can write according to this step? That is a good approach actually. There is an x p of x. So we have to check predicate for 1, then for 2, for 3, for 4, and you can write them with this disjunction and check all these values because there are only 4 values. So for 1, what is that? 1 square only 4 square 16 greater than 10. Then it would become what? Only for 4 it will become true. Okay. 16 greater than 10, true. And for the rest of the values, false, 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 true. So that's why now you are mentioning P of 4, P of X is true for this value 4. So we need only one evidence to make this theory true. So that's why we can say there is an X, P of X is true. Because we have found that evidence. Now, precedence of quantifiers. Precedence, now you understand from the previous CO2 that what means precedence. Precedence of logical operators. You have seen that negation has the highest priority. After that, conjunction, disjunction, and then single arrow, then double arrow. Single arrow means implication. Double arrow means by implication. So now that is the same topic, precedence of quantifiers. So precedence of these two operators is always higher than all the other operators that you have studied before. You have studied before conjunction, disjunction, all those five. But if you have these quantifiers in the mathematical expression, in the logical expression, these two has higher priority. You have to solve them first. For example, here, if you have something like that, for every x and p of x or q of x, then this quantifier is with this part, not with that part, okay? Even the variable is x here, also x here. So you don't have to confuse yourself. So precedence, quantifier precedence. So this quantifier is with this part, the first part. You don't have to, there is no, if there would be parentheses like that, if there are parentheses, then this quantifier is with both. So then the quantifier is with both. If there are no parentheses, then this quantifier is only with this part. Even the variable is same. So here I am saying that this means this and not this, okay? There is an example 17 about finding the precedence of quantifier. That is example 17. Read it by yourself. That is easy. Now, binding of quantifier variables. Binding. There are three terms that we will use: bound variable, free variable, scope of variable. These also exist in programming languages. All the things that you study is also exist in programming languages. Bound variable, any variable x or y or z or whatever which is attached with a quantifier. That quantifier can be universal, can be existential, which is any variable which is attached or used with a quantifier. That variable would be called what? Bound variable. For example, here this variable x is what? Bound. That is bound with the quantifier because this variable is attached, is used with the quantifier. But this variable, that is not the, it is out of scope. If it would be y, for example, then there is no any quantifier with this y variable. So then you can say, then this is called free variable. So for what is free variable? A variable that is not used or bound with a quantifier, or there is no any value set to that variable. If you have not, and if that variable has no any value, or the other is are not linked with a quantifier, then that is called free variable. We will understand with examples all these things. But first, take these definitions. Scope of the quantifier. So if in any logical expression, if you have a quantifier, you have to look that which part of that mathematical equation to which part that quantifier is linked. And only that part would be called the scope of that quantifier. So the part of the equation to which a quantifier is applied is called the scope. Let's see that with the example. So now if you have this statement, now find these bound, free, and scope, whatever. So this x, there is an x, and then x plus y is equal to 1. And here this x is a variable, and this existential quantifier is attached with x. So then you can say x is bound variable. And this y, there is no any quantifier for this y. And here parenthesis starting from here, ending here. Ending here, the parenthesis. So this quantifier has this whole part as a scope. This whole part, what is the scope of this quantifier? This whole part within the parenthesis. In this part, this existential quantifier can affect this whole part if you will use this variable anywhere. if you will use this variable x anywhere, anyhow. But this x is bound variable because this existential is used with this x. With this y, we have no any quantifier used, and we have not assigned any value to this y. So that's why this y is what? Free variable. This is what? Free variable. Now, here, I'm going to previous example to give you the scope of quantifier. Let's see this example. What is the scope? If I ask what is the scope of this universal quantifier, then you will see only this part, because because what, you have to see precedence also. This quantifier is used only with this predicate and not with this predicate, and not with, if you will use for every x again here, then you can say. But here the scope of this universal quantifier is only this part, not that one, not that one. But if I will give you this equation, this question, and if I ask you what is the scope of this quantifier, now due to these parentheses, the scope is the complete, yeah, the complete part. Okay, example 2. Here in the statement, by the way, it is written here, read it by yourself. So read it by yourself. Let's see it if you want. So there is an x, p of x and q of x, or, so these are the parentheses. This is one part, disjunction, this one. So this existential quantifier is used with x. X is here, and the parenthesis is here. So this existential quantifier is, so this variable x is bound, huh? And here r of x, this variable x is also bound by this quantifier. So that's why you can say the all variables here, this x is bound, this x is bound, this x is also bound. This x is bound because it is the part of, due to these parentheses. So that's why you can say all variables are bound. Yeah, and then for the scope, okay, let's see what is the scope of, what is the scope of this? The scope of this is this part. And the scope of this universal quantifier is this part. This is written here. Okay, I think up to this point, I am going to end this.